55 kilogram box is on a horizontal surface. The surface has a mu s of 0.32 and a mu k of 0.23. Can you tell me what mu s stands for? That's right, that's the coefficient of static friction. Can you tell me what mu k stands for? It's the coefficient of kinetic friction. These two coefficients are different in what way? That's right, static means it's standing still. Kinetic means that it's actually moving. So the static friction is the friction that the object feels when it's not moving, and the kinetic friction is the friction that the object feels when it is moving. So it's two different frictions. Tell me, if I wanted to find the actual value of the static friction, so how many newtons of friction that it'll give you, what's the formula for that? Very good. Mu s times the normal force. Now, if I wanted to find the value of the kinetic friction in newtons, how would I do that? Yep. Mu k times the normal force. Tell me, what is the normal force? What's the equation for the normal force? Exactly. The normal force, which is the same as the weight, is equal to the mass times gravity. Very easy. So let's find our normal force first. What is the normal force, or the weight, of this 55 kilogram box? 5 times 9.8 equals, so this Fn is equal to 539 newtons. Let's go ahead and solve for these two separate values right here. Our static friction force and our kinetic friction force. (0.32) times our Fn, which is 539, and our Fk is equal to 0.23 times 539. These will give us two separate values, each relating to their own frictional force. So, we have 172.48 newtons of static frictional force, and then we also have 123.97 newtons of kinetic friction force. Now, again, tell me, what is the difference between static friction and kinetic friction? Good job, yes. The static friction needs to be overcome for the kinetic friction to actually start happening. So let's draw a table right here and let's show that. We have our force applied, whatever that may be, our static frictional force, our kinetic frictional force, and then our net force that the object feels. Our static frictional force is massive. It's 172.48 newtons. That means that for an object to overcome it just standing still or being at rest, it has to have more than 172.48 newtons of force applied to it. Let me show you this. If I apply 50 newtons here, the static frictional force is going to apply 50 newtons back to me. Why is that? That's right, it can only apply 50 newtons of force back to me because I'm only applying 50 newtons of force to it. There's no possible way, even though the static frictional force has a value of 172.48 newtons, it can't apply more force than I'm actually giving to it. That would mean that if I'm trying to push the box, it's actually moving me backwards, which doesn't make sense. Since it's not moving, there's no frictional kinetic or kinetic friction, and since these two cancel each other out, there is no net force. Let's look at it like this. What if I do 200 newtons? Is 200 newtons larger than our static frictional force? Yes, that's a very easy question. Yes, it is. If that's the case, bless you, Mr. Perkins. If that's the case, and it's larger than this value right here, then that means that there is no more static frictional force applied on the object. If it's moving, this value that we write in this table automatically drops to 0. 0 newtons. Now, can you tell me how much kinetic friction is actually applying on the object when it's being pushed with 200 newtons of force? That's right. When it surpasses the static friction and it moves into kinetic friction, the kinetic friction stays the same no matter what. So the kinetic friction is actually applying 123.97 newtons of force back onto the object. So what does that make our net? If we're applying 200 newtons of force to an object and it's pushing back at us with friction with 123.97 newtons, is our net force going to be larger than 200 or smaller than 200? Easy question. Yes, smaller than 200. So let's do 200 minus our kinetic friction force. And we'll end up with 76.03 newtons of force net in that scenario. Great, so I'm going to erase this, and let's actually look at what the problem's asking us. The problem is asking us, let's look at letter A right here. What is the minimum horizontal force needed to move the box from its resting position? Well, we just discovered that in our table. What is that minimum horizontal force needed? You're right, it needs to be 172.48 newtons. So for letter A, FA needs to equal 172.48 newtons. I know it's the same, and it might sound weird, but for the purposes of this class, this value right here, whatever you get for Fs, is the amount that you need to push it by to overcome the static friction. Okay, great. That's the answer to letter A. Now, letter B is a completely separate question, right? Letter B is asking, what is the acceleration of the box when a force of 79.88 newtons is applied in the horizontal direction? 79.88 newtons is applied. Interesting. If I apply 79, so our FA, I'm actually going to even erase this. Forgetting letter A, it's a completely separate question. If our FA is now equal to 79.88 newtons, does the box move? Yes or no? You're right, it doesn't move. Why does it not move? You're right, it doesn't move because 79.88 is less than our threshold value of 172.48 newtons. If our box cannot overcome the static friction force and it doesn't move, what is the acceleration? Acceleration is 0. It has no acceleration. A is equal to 0 meters per second squared. It has no acceleration because it can't overcome the static force.